Good afternoon. Welcome to the Breaking Ground session. My name is Fabricio Bortoluzzi, and I will be presenting this cloud telescope research to you in the next 40 minutes. Thanks for choosing this track among so many awesome tracks out there. I hope audio is clear. If audio is not good enough, please shout, complain, and I will address. Well, my name is Fabricio, and this is a presentation on this cloud architecture called Cloud Telescope, and it allows for observing internet-wide activity. In this case, the presentation today refers to describing malware spreading activity, botnet spreading activity, as part of the results we can find with this development and research. This is myself. I am a computer scientist. I currently work at Noroff University College in Norway. And it's quite nice to be here in Las Vegas, much warmer. I am a cloud solutions architect. I teach cloud computing and cybersecurity for undergraduate students, among other activities that I hold. And this is part of the research myself, Barry, Lucas, and Carla have been doing for the last 3 years. I have 5 topics to show you: internet background radiation, the standard network telescope, the cloud telescope, the experiments we have been conducting, and the discussion of these botnets that we have been detecting by the method. Not sure if you're familiar with this terminology. Internet background radiation seems like a fancy terminology, but it's pretty much an analogy to describe all the often malicious activity we can capture by capturing unsolicited packets, either on a domestic router, a standard unfirewalled host, or in this case, a sensor network that is deployed within cloud service providers. By analyzing this, we can learn from vulnerability scans activity, we can learn warm botnet propagation, and more recently, even benign scanners such as Sensis, Shodan, and much more. The backscatter is one of the most prevalent activity found in internet background radiation, in this wild traffic that you can capture as long as you don't filter using mechanisms such as a firewall. We can say that this intense activity arriving to internet-connected hosts happens all the time. It's low intensity. It's not really a huge bandwidth concern. And it has been studied for at least 20 years, mostly in a research center very close to Las Vegas, within CAIDA, the Center for Applied Internet Data Analysis here in the United States, mostly held by the Internet or the Network Telescope deployed at the University of California, San Diego. They are our benchmark. They are our reference to the work that I have been conducting. Vulnerability scans, you know what this is, but this is also something you can capture if you deploy sensors to listen to the internet background radiation. You can learn how noisy it is, how frequent it is, and the most attacked or most scanned ports, so that you can start to trace some sort of behavioral pattern, not affecting a specific company or a specific web server, but affecting the internet at wild, gross, if you will. It's mainly malicious activity, as I said, but also the newer internet census tools have been changing the pattern of this traffic as captured by the method, especially Shodan and Sensis. Worm infection is also something that researchers can learn by listening to the radiation. We can learn how frequent they are, what are the most scanned ports or infected ports. This type of research led to the quantification of how bad Code Red was at the time. Blaster, Sasser, these are old names for sure. And let's say mid-2010s, Configure as a major malware spreading activity that led to major problems at the internet. at the time. Botnet activity has becoming of growing interest starting around 2015. Botnets, of course, are networks of computers infected with malicious software, aiming at remote control of the infected device, ultimately leading to attack orchestration, most of the time against famous targets, such as big companies, more recently GitHub, and many other companies out there. So radiation, or this internet traffic pattern, has been changing from malware-centric to botnet-centric according to our observations and according to CAIDA's telescope. And that led to the following research interest. What if we could listen to this traffic and describe the patterns effectively used by this botnet infection and the most vulnerable devices, even though there are many devices out there, if we could profile them, what would be the most relevant characteristics? The field is completing 20 years of active research. If you would like to join this field, there are many ways to join it as a bachelor's student, master's and doctoral level or PhD level studies. It's ultimately an interest of scientists, the cyber security industry, armed forces many times, because it seems there is a geopolitical influence driving many types of attacks. The network telescope is the standard mechanism. This exists for nearly 20 years. Usually businesses deploy firewalls to protect against the most obvious malicious activity. In this case, it's the very opposite. We want to let traffic in on purpose, unfiltered, and to that machine, the more IP addresses you can bind to the device, the better. Huge telescopes can listen to, let's say, an entire /8, 16 million packets. The newer telescopes only listen to a fraction of this amount, sometimes the equivalent to a block C network, a /24, 200 hosts, something of the sort. That's related to how scarce IPv4 addresses currently are in comparison to previous times. So that's a machine. This is usually built with FreeBSD, Linux, TCP dump, IPFW, Linux default firewall if you prefer, and TCP dump actively records, passively records, better saying, passively records the incoming traffic. Most of the times it won't answer back the traffic, so it's passive. Sometimes you can implement a honeypot-style behavior, and then you will capture application layer messages exchanged with the sensor. So methods vary. Most of the time, researchers only want the incoming traffic so they can profile it. Not even answering the TCP three-way handshake is a priority to these studies. The network telescope is passive. It doesn't respond. Traffic's allowed in. It's usually deployed at universities, probably mostly related to people trying to learn from this cyber threat acquisition mechanism. So far, so good. Any question real time? Okay, leaving it for later. And the cloud telescope. This is our contribution to the field, mine, Barry's, Lucas, and Carla's. The idea is that instead of deploying a single telescope in a single region of the globe, such as the University of California in San Diego, at Rhodes in South Africa, in São Paulo in Brazil, we want to deploy a fleet of sensors that will distributedly capture the traffic so we can learn if there is some sort of geopolitical influence over the type of traffic that hits the United States versus the traffic that hits Norway or China or any other country. The reason is that cloud service providers currently enable us to deploy a distributed fleet that is budget-friendly, that allows one to launch worldwide sensors without having to move from their chair, meaning deploying via software instead of deploying a physical computer as it's usually done. The cloud telescope is described by this architecture containing the internet gateway router and a forcefully open security group. We have to open all ports, allow all traffic in, and then the sensor is deployed there. For example, in the United States, in AWS, you can cover 4 different regions of the country, 2 in Canada, 1 in Brazil, and so on. That's how the cloud telescope can be deployed. Traffic is recorded in PCAP using a demonized version of TCP dump. Recordings are rotated and loaded to a cloud bucket so that recordings are centralized instead of distributed across the many telescopes out there, and it makes it easier for later processing the data. Common tools and stack that is used. T-Shark is the de facto standard for dealing with largest amounts of PCAP traffic. If you just want a sample that contains less than 1 million packets, it should be okay to look at it on Wireshark for small samples, for learning in a more friendly way. And you can also index packets using very interesting new security stacks such as Security Onion or the well-known Elasticsearch and Kibana frontend to interact with the data and eventually learn new patterns from this indexation. Radiation looks like this, standard PCAP, because it's a distributed sensor fleet. You can see, for example, in one, Census scanning our sensor. In two, you see Shodan. And this quickly appears, so you can even profile how frequently friendly Census tools are scanning the sensor fleet. In a 3, you see some sort of distributed backscatter. It's backscatter because TCP is resetting the connection. We didn't initiate that connection, but it looks like we did, which is the very definition for internet backscatter. And it's ultimately interesting to learn from this unexpected traffic. You can see in one, public scanners are out there. In two, many ping requests arriving from sensors in another region of the world. In this case, it's a US sensor being queried with ICMP packets coming from Amazon in China. You can see old style SIP asterisk VoIP attacks using UDP communication on the SIP port. And that's how a sample looks like. The architecture is deployed as this. We were able to capture this traffic during 45 days last year. At the time, AWS had 26 commercially available regions. Each one of the regions was added or contemplated with 10 sensors, 10 EC2 virtual machines, each one tailored to be as small and cheap as possible so we could keep the experiment running for the largest amount of time. There is no need to keep the architecture running after the capture. We made use of the cheapest price model made available by AWS, which is called the spot pricing model. Using this, one can save up to 70, sometimes 90% of the standard costs related to a sensor, but you are making use of the idle capacity of the cloud service provider. Therefore, you have to handle an instance termination notice, meaning that your instance can be destroyed if you no longer wins the bid for having that instance allocated to your account. So we implement some sort of listener that will launch a new sensor upon termination request. Terraform is used to describe the architecture, so anyone wanting to reproduce the experiment can do it. And Bash is used for automation, and that's how it's usually deployed. We use Alpine Linux because of the smaller footprint. This is related to the fact this distribution doesn't implement a full glibc userland library. It implements a much tighter, smaller footprint middleware, meaning it can operate with half a gigabyte RAM virtual machine. And that's the main characteristics of the device. Whenever we receive the termination notice, we'll stop the capture and launch a new one. Imagine you have up to 260 virtual machines, 10 per AWS region in this case, and they are capturing and recording unsolicited packets arriving to the sensor. That's the first takeaway of this methodology. The ephemeral nature means that it exists as a Terraform artifact. The GitHub repository is maintained by Lucas Baylor. And that's where the results I'm going to present come from. We deployed 260 sensors in AWS. Starting August, we wanted to keep it running, let's say, for 6 months. But after 45 days of capture, even though we weren't serving no service, 10 billion packets were captured. We had to stop because this was becoming quite huge to process. It resulted in 200 gigabytes of PCAPs that anyone out there can download and do your own studies. There are many patterns there that we only know exist. No one ever got into them to see what they really look like. We are still looking for answers on, is there any sort of geopolitical influence affecting the attack patterns we capture with the telescope? This is an open question. And for this experiment, one key characteristic is that for ports SSH, Telnet, Web, and HTTPS, Lucas implemented some sort of application layer responder, answering back to attackers. If they wanted to get into the machine, they could do so. But we were actually recording their commands upon infection, other than really exposing a vulnerable shell back to the attacker. So that's one key characteristic that makes this presentation unique. What does one learn if one launches such an architecture? What did we learn for 45 days after capturing 10 billion packets? According to the experiment, 98% of the unsolicited traffic arriving to the sensor fleet was TCP. No footprints of denial of service attacks or any other form of UDP exploitation or ICMP flooding were saw only by a very small extent. Most was TCP. We captured almost 1 million IP sources from all parts of the world, which I will profile to you in a minute. That's the range of if you could call it the telescope resolution or aperture, that's what we can learn or see by deploying it currently. Even though I only launched 260 sensors, they were recycling their IP addresses according to AWS policies, and therefore we had 603 IP addresses captured on our side as honeypots. Traffic distribution across the world was fairly even. The baseline here is 4% per region. Asia Pacific Southeast 3 saw 6%, and Asia Pacific Southeast 2 saw only 1%. The most attacking countries, not from an AWS perspective, but by the country that owns that IP address or the country that is linked to the radiation source. We saw the Netherlands as the most prevalent country. And there is a curiosity there. Can you imagine the reason why Netherlands is the most apparent source of these random attacks arriving to the sensor fleet? Sorry? It's coming from many anonymization services, VPN services. They have a culture of hosting these services. This is openly available, but that's the pattern. Openly available anonymization services, including VPNs. That's our guess. We cannot fully endorse the statement, but that's what it looks like, considering the autonomous system number holder, the owner. attacking source was Taiwan, Thailand, Pakistan, Poland, and so on. The most frequently attacked sensors were residing in the United States. This is slightly biased in the sense that the United States has 4 AWS regions, 4 different places. We had 40 sensors in the country. But even if you split by 4, you will still see some sort of average activity hitting the US. The least attacked sensor fleet was in Germany, Canada, and the United Arab Emirates. But it's also fairly even, with a small bias towards the US and India. If I had to tell you in 2024 that the most attacked TCP port is actually the Telnet port, this would be like big news in the 90s, in the early 2000s, but it's still the most prevalent. I would say there was a shift around 2015. It wasn't the most prevalent according to Kaida's telescope, but it has become the most attacked port by far. Do you have a guess on why Telnet is currently the most prevalent destination port for random attacks? It's a 3-letter IoT. Thanks for the answer. Precisely. Meaning the IoT introduced a new generation of low power, low cost, fast time to market devices that are not necessarily as secure as modern operating systems. So that's our conclusion to the why. But as you can see from the patterns that I'm going to show you, it's actually exploiting Linux kernel 2.2, 2.4, which are highly related to embedded devices, not really ordinary servers. Followed by GTA, but to a far less extent, Minecraft, VNC. Really interesting to see VNC exploitation as a top target. And then the classics, SSH, HTTP, DNS over TCP, which is not really the common standard, SMTP, and so on. RDP is also there. If you think about the UDP exploitation, it mostly relates to the recent LDAP vulnerabilities that are actively exploited. And of course, the amplification attack related to Memcache. Redis, which is connected to some of the talks presented earlier today, is also there. And also DNS and the classic, often exploited ports. ICMP is mostly ping, 99% of the times, echo request, echo reply to a far less amount, and other not so popular ICMP types being captured. When it comes to ping flooding, the most active source was actually China, followed by the United States. So speaking about profiling the source of the attack, the IP sources really belong to companies in the Netherlands that hold business related to anonymization. They sell anonymization services most of the time. Belgium also shows up there, followed by China and Japan. That's the profile. In all cases, this is probably tunneled before hitting the sensor using some sort of GRE encapsulation or any equivalent protocol. Now, speaking about the malware analysis, let's analyze it together. Let's see if we can decode together. This is text version of Wireshark T-Shark. We can see at the application layer, well, it's TCP at the transport layer, source port not, in this case, it shows reversed. Source port is actually 39,000, mostly irrelevant, but destination is 23. The honeypot records any command that the attacking source wants to inject without actually executing the commands, but acknowledging, saying, yes, you were successful with the command, proceed. That's how it pretends to be. It starts with an attempt of running a wget script that we can assume will try to download some sort of payload with the infection commands, control and command, or turning the target into a zombie, very likely. This also reveals the vulnerable server, often vulnerable server serving the payload, so we can also study who is out there vulnerable, serving payloads for attackers on the internet. Eventually, it's just an unprotected website that got hacked and they are the apparent source of the attack. Many times it asks for some sort of BusyBox exploitation. They hope our honeypot runs BusyBox, which reveals the embedded nature of the attacker's expectation upon the target. We can also see trivial FTP. This is not really FTP, but a variation, trying to download data from somewhere else, trying to run shell scripts related to the TFTP download, attempts to execute BusyBox, FTP get. From an attacker's perspective, this is an attempt to ensure that they have really infected the machine and turned them into a zombie. We also see curl, and then connection attempts arriving next on the next packets. So that's pretty much the way it looks once you deploy the telescope and start learning their attack patterns. Now let's go into some binary analysis. We want to know which binaries are most frequently linked to the payloads being delivered to the honeypot. The names are not really the most exciting ones. This one calls I, but you can hash the binary and compare it against publicly available sources, and then you learn exactly what this binary wants to deploy, what is its intent. And then you see many funny names out there, but notice one pattern reinforcing the IoT behavior. It's most of the time 32-bit binaries, or they carry the 86 appendix. The attacker can call it as they want, but it reveals some sort of pattern. And then we can link the binary with the very botnet. In this case, it's the botnet profiling. And the botnets are, I believe this is popular names by now, right? Mirai, is it popular? Have you heard of Mirai before? It's probably the most active botnet on the wild. They're not really aiming at a single target, but they are the most prevalent in quantitative terms. And there are many variations out there, including Mozi, detected 10 million times in the experiment, quite frequently, and Sora, among other names. We can try to learn how many strains are out there. And by learning from where they are downloading the payloads from, we can try to guess if they belong to a same hacking group, or if they could belong to different hacking groups, deploying their botnets for later use against targets. In all cases, for the top 10, they carry a 32-bit signature. They are often related to embedded systems. After probing the honeypot, if it's attacking port 80, it won't speak shell commands. It will speak HTTP commands, right? In that case, we will see gets, posts, and this kind of pattern. In this experiment, 6 million times, Mirai was trying to infect the honeypot with this single source, 185.224 something, hosting the Cutie binary. To a smaller extent, Mirai again, Mozi, they were the most prevalent ones. So these are the busiest sources serving. If we were to quantitatively tackle the problem, we should start by addressing what's going on with the services. What are the vulnerable services exploited by attackers that we should promote awareness about? The commands also reveal what kind of vulnerable service, HTTP-based service, could be running on the vulnerable hosts. Many times it's an attempt to get the environment variables. It depends on the type of technology used, either a Windows server with IIS, a PHP server on an Apache, many other options. You see predictable patterns, a lot of exploitation, trying to leak GitHub or Git authentication credentials. This is the kind of cyber threat intelligence acquisition you can get by running the cloud telescope. Of course, because this is deployed in AWS, we could expect a lot of health checks coming from the cloud provider itself towards the web ports 8443. But to a smaller extent, in other cases, it was these projects. This also reveals that, for example, Palo Alto has a project related to mapping the internet. It's benign, it's not an attack, but it's interesting to quantify. Another cloud mapping experiment at pdrlabs.net, this is unknown to me. Census is inspecting port 80 and signing, because this is totally upon the attackers to rewrite as they want. This is not a standard that must be followed truly. And of course, Python browsers or mappers, Go mappers much faster. So this is, again, something one can learn. Now, if we were to speak, okay, you detected a lot of binaries. We see that it's an IoT-style infection. But what else? We can tell you that in this experiment, I think CVE, this is related to embedded CCTV devices. From an attacker's perspective, it's a good business to launch infection attempts against CCTV, as they are generally the most vulnerable, followed by a CMS system used mostly in China, Think CMF. I only knew about it by trying to reverse engineer what was going on. Also Totolink, which is behind billions of IoT devices, a common middleware used for anyone wanting fast time to market IoT devices. According to the insight here, the most popularly exploited systems are IoT systems currently, according to the method, and they're exploiting highly critical vulnerabilities, which goal is to increase the fleet of botnet sensors on behalf of the attacking group they belong to. So expanding the zombie fleet, if you will. That's the conclusion. That's what you get by analyzing unsolicited traffic arriving to a sensor fleet on a cloud-based experiment. We have many questions if you want to help us to find better answers in terms of geopolitical influence. But okay, this is botnet expansion, but is there a political intent behind the attacker? Is it a nation-sponsored attack, or is it just an ordinary attempt for business, for money, for profit? Both could be true. We need to investigate. Here you will find the most relevant links. We also have companion publications. If you want to learn this from a more academic research perspective, it should be interesting for both worlds. The research community, but also the industry should have an interest at the results we have been finding, and there is, of course, more to come. That's all. Thank you very much for your time. Thanks again.